let's get started. So this lecture, we're going to be talking about JAX, which is a Python library. Hands up who's heard of JAX? Okay, most of you. Hands up who's actually actively used JAX? One person, yeah, okay. Good, so it's something you've definitely heard about, I'm sure. And it's a library that I'm using a lot now in my research. And I think a lot of people who are carrying out scientific machine learning are using libraries like JAX to carry out their experiments. And so the purpose of this lecture is to give you a high-level overview of what the library is and why it's useful for all of the kind of techniques that we've been studying so far. So, you know, coding up and training things like neural operators, physics-informed neural networks, hybrid workflows, these sort of things. So we'll hopefully spend the first half of this lecture talking about JAX, and then I'll try to move on to symbolic regression. We're a little bit behind, so I won't finish symbolic regression this lecture. We'll move on and cover it on Friday as well. Okay. So I'm going to be explaining to you what JAX is. I'm going to be talking about the core kind of functionality of JAX and how it's maybe a little different to other deep learning or auto differentiation libraries like PyTorch and TensorFlow. I'll do some live coding, and then I'll also talk a bit about how we can use JAX for SciML. So you should, by the end of the lecture, hopefully have a basic familiarity with JAX. Understand what this core idea of JAX is, which is a thing called a function transformation. I'll tell you what that is in much more detail. And then be aware of how you can use JAX to work on these scientific machine learning algorithms and research questions. So what is JAX? I already said JAX is a Python library, and it simply does these two things. One is accelerated array computation. So this is JAX is extremely fast array computation, so basic kind of linear algebra computations. And it allows you to do that not on the CPU, but also on the GPU and fully exploit the parallelism of like our modern GPU devices. It also has this really amazing feature, which is program transformation. And this is kind of the heart of JAX and how JAX is designed. So we'll talk about why this is such a powerful idea coming up. But these two things combined together makes it very easy and very powerful to design kind of these high performing, highly scalable scientific machine learning algorithms, or even just ML algorithms, or even just scientific computing. It doesn't have to be both at the same time. So just to give you some motivation why JAX is interesting and why a lot of people are using it now. JAX has been used to build some of the biggest machine learning models. So it's developed by Google. And so a lot of the kind of Google's biggest products and research are built in JAX. So I imagine everyone's heard of Gemini. This is Google's recent LLM model, large language model. So this model was trained in JAX and used all of JAX's kind of functionality to train that model across thousands of GPUs and really scale the training. Also AlphaGo. So this is, again, DeepMind's algorithm that was able to play chess and Go and other games extremely well and exceed human performance. This was a massive kind of breakthrough a few years ago. So the underlying algorithm behind this is a Monte Carlo tree search algorithm, which has some kind of learnable components to it. And again, this kind of advanced kind of search algorithm is written in JAX, and there's a whole implementation that you can look at on GitHub for it. JAX is also being used a lot in scientific computing today. So here's just 3 examples of kind of state-of-the-art libraries. So we have another library from Google, which is AlphaFold. So I imagine, has heard of this. This is the model that is able to carry out accurate 3D prediction of the structure of proteins. There's also Brax, which is a library which is able to do kind of robotic, rigid body simulations for reinforcement learning, typically. So this is being heavily developed and contributed to. And then there's a lot of papers that are coming out using JAX to do, scalable scientific computing. So this is a simulation of the ocean surface velocity simulated in 24 hours across 16 A100 GPUs. So this is like state-of-the-art GPU simulation of climate dynamics. And again, this paper used JAX to implement this model. Okay, so that's kind of a I guess it's a sales pitch for why JAX is useful or is being used right now. So what I want to do is get into the library in a bit more detail and tell you why people are using this to do scientific machine learning tasks. So first, I'm just going to talk about the accelerated array computation. So this is something that other deep learning libraries, PyTorch, TensorFlow, also do very well. But JAX is just the same. So what's nice about JAX is you can somehow think of it as just NumPy on the CPU and GPU. So one of the core libraries inside JAX, or one of the core modules inside JAX, is jax.numpy, and you could just think of this as basically a JAX version of NumPy, and the kind of syntax is exactly the same, or tries to be exactly the same. So to be able to port NumPy to the GPU, or to basically to run these fast like linear algebra computations of arrays, JAX uses this thing called XLA, which is accelerated linear algebra. So this is a software that compiles the code, the JAX code, and allows it to run very fast on whichever device you're using, whether it's the CPU or GPU. I'm not going to get into the details of how XLA works. You can just think of this as the kind of core engine that makes stuff fast in JAX. And the program transformation. So what is brilliant about JAX is it allows you to kind of also carry out autodiff and also automatically parallelize your code and compile your code as well. And all of these things could be thought of as a transformation of functions. And this is what really what makes JAX very powerful for our kind of scientific computing methods. So I'll go through each of these in turn later. So let's just talk about accelerated array computation to start with. So yeah, JAX is simply, or can be simply thought of as NumPy on the GPU. So on the left, this is some very standard NumPy code. I'm just defining a matrix and then doing a matrix multiplication and printing the output. And hopefully everyone's very familiar with NumPy and how it works. And you can just see when we import jax.numpy, the syntax is exactly the same. So we define an array in the same way. We can use the same kind of matrix multiplication operators, and we get obviously the same result. Okay, so all the other functionality in NumPy, like numpy.sum, numpy.arange, all this stuff is also in jax.numpy and defined the same. So what's interesting though is that the JAX code will run on a GPU. If your system has a GPU device, this is what makes JAX different to NumPy, because NumPy is just defined for the CPU and highly optimized for CPU devices. And so what's great is that if this is a really large matrix multiply, for example, so if I do a matrix multiply in NumPy, so this is 10,000 by 10,000 matrix multiply. NumPy, that takes about 7 seconds just to do the matrix multiply on my MacBook computer here. If I do the same thing on a NVIDIA GPU using the JAX code, it's 126 times faster just to do that single matrix multiply. So can anyone tell me why running a matrix multiply on a GPU is faster than a CPU? Cool. Yeah. Yeah, because you can do all the row and column products on the same time. So why exactly? What is it about a GPU that lets you kind of parallelize? That's how GPUs are built, yeah. Anyone know? Who knows what the architecture of the GPU looks like, or how does it look different to a CPU? Go on.
It's like hundreds of little cores.
Yeah. Yeah, so CPUs, so here we go. So I just asked this question. So CPUs and GPUs, this is a very high level sketch of what the actual device looks like, the hardware looks like. And what CPU, you can think of CPUs as just consisting of a small number of cores. You know, a laptop might have 16 cores or 32 cores, say. And these cores are designed to be incredibly fast and really, really good at serial computation. So that's sequential computation. That's computation that depends on its previous inputs. And these types of computations are the ones that we usually need when we're running like an operating system on a computer. We do lots of tasks in sequence. And that's what they're designed for, and they have very low latency, and they're really good at these tasks. GPU, on the other hand, you can think of it as having thousands and thousands of cores instead of just a few, like 10 or something, or 16. And they are designed for running computations that are highly parallel. So, you know, the same computation that can be done across all the cores, and then that computation can be collected and output by the GPU. So they're designed for parallel processing, and they're designed for high throughput computations. And you know, originally NVIDIA GPUs, or NVIDIA as a company, was like focused on game development and the kind of computations that you need to render games. But it just so happens that GPUs and these kind of parallel computation is exactly what we need when we're doing kind of linear algebra computations. Yeah.
We should have a lot of let's say 4 cores.
What do you mean by overhead?
Like the latency for the communication that
Yeah, I actually think the communication is faster because the cores are, you know, on the device, so the readout is incredibly quick. I think when you have multiple CPUs, it can, if they're on, you know, on different nodes, then it can take much longer to communicate between them. I mean, it's worth testing. But I would imagine a GPU would be a multi-threaded CPU for a matrix multiply, given how optimized these devices have become in the recent years as well. Yeah, so it turns out pretty much, you know, a huge percentage of the computations that we do in deep learning. Remember, I was talking you through autodiff, and it just turns out to be a lot of matrix operations. They are very well suited for running on the GPU. We can do those matrix multiplies in parallel, or at least all that we can multiply all the elements in parallel before we sum them. Yeah.
Do you somehow have to tell JAX which device to use, or just tell matrix?
Yeah, so JAX knows which device you're running on. So if you have a CUDA installed and you install the CUDA version of JAX, then it will automatically look and use those devices by default. So I don't even have to, I know in PyTorch you kind of have to define which device you have. In JAX, you don't even have to do that. It just knows which device you have.
You have to install the right version.
Yeah, you need to install the CUDA version. Yeah, it's very simple to do. Yeah.
Let's say if you have a program in sequential theory,
Yeah.
JAX, but then it's on the GPU, then it's slower.
Yes. Yeah. So the question is, if you have a sequential program, or one that, you know, operates on a single value, like a scalar value, and then does a lot of sequential. Yeah. So then I would agree with you that GPU is not ideal for that, and it would likely be slower. So you do have to think about the types of tasks that you want to put on the GPU. So JAX.NumPy also runs very fast on the CPU. In some cases, faster than normal NumPy. So it may even still be fine to use JAX. I have an example of that coming up. Yeah.
Does JAX support A and B?
That's a good question. I think so. So XLA, which is the backend, which compiles all the code down onto the GPU, I think it supports quite many different GPUs, not just NVIDIA ones. For sure, it supports TPUs, which Google's accelerator. Yeah. Okay. So yeah, I want to make the point, or I want to argue the point that a lot of the kind of scientific software that we use does indeed use, you know, matrix multipliers or like matrix operations, or tensor operations in general. And it's not just our machine learning workflows, it's like our traditional scientific workflows too. So this is a finite difference simulation of the wave equation. So this is a fairly high frequency, large kind of simulation of these waves propagating through an Earth model from some source here. And this is the code to actually run that simulation. So you probably can't see it in detail. It doesn't matter that you can't read each line for line. But what I've got on the right here is just a NumPy implementation. And this is a finite difference scheme. So what that involves is just, starting with the initial wave field and then doing finite differences on the wave field to numerically solve the PDE. And so the finite differences do things like taking that wave field array and then subtracting it with itself, but shifted by 1. And that's obviously a big matrix multiplication that we can do in parallel. That's a kind of element-wise operation. So this is kind of what all this intermediate stuff is doing inside this for loop of this finite difference scheme. So I can do the same thing in JAX. So there's a lot of element-wise matrix operations. So you could see how this lends itself very well to running on a GPU. The GPU could do each of these element computations in parallel on all of those thousands of cores. So what we can do is just rewrite it in JAX. So we just import jax.numpy instead of import numpy. And in many cases, it can just be as simple as that, depending on how you've written your NumPy code. The JAX code can look incredibly similar, if not the same. So you can see how similar this JAX version is. We're using, again, jax.numpy looks like NumPy. So the padding operations, they have the same inputs and outputs, for example, all the other function calls as well. The only thing that we change is at the bottom here, instead of doing a for loop to kind of update the wave field through time, we do a lower level call, which is called jax.lax.scan, which essentially implements a for loop, but allows that for loop to be compiled and run faster than a kind of a native Python for loop. So this is more of a technical detail of JAX. It's important to understand this, but I can tell you more about that later if you're interested. But what you need to take away from this slide is it can be just as simple as replacing your import statement to change your code into JAX. So once we've done that, we can then run that wave simulation on the GPU. And so here's the runtimes of the comparison. So this is NumPy on the GPU. And I've tried to fully optimize this NumPy code. So NumPy tries to use this kind of vectorized computation. So I try to remove as many for loops as possible. This is what makes array computation slow in Python. So I optimized this as much as I could. And so this ran on my MacBook with 8 seconds to do the whole simulation. Now I can take my JAX NumPy code and compile it. And so this is an extra feature that JAX lets us do. And once I've compiled it, this runs 1.5 seconds. So this is already 5 times faster just with a compilation on top of the NumPy code. So this kind of helps to answer your question that it can be faster on the CPU if you do a compilation on top. But the amazing thing is when it runs on the GPU and it's compiled, it's 123 times faster. So we're going from kind of an 8-second simulation down to a 65 millisecond simulation, which is kind of impressive, like given how high high frequency or fairly complicated this simulation is. Okay. So hopefully I've argued that JAX, but just like other libraries like PyTorch and TensorFlow, allows you to run these kind of linear algebra computations on the GPU and really accelerate them beyond what we can do on the CPU. Any questions so far? Okay. So the next thing I want to talk about, which is the really interesting thing for me, is JAX's program transformation ability. And so this idea is what allows JAX to do things like auto-differentiation and auto-parallelism, parallelize your computation across many inputs, without you having to write any more code. And this is probably the most powerful thing about JAX, and this is why it's so useful for using it in these kind of SciML workflows. So hands up who knows what a program transformation is, or a function transformation. Okay, so a new concept. So what is a program transformation? So let me just write a very simple function here in Python. This is just a function that takes x, the value of x, and it returns x squared. So a program transformation, or in JAX, looks like this. And this is a program transformation that turns that function into a new function that, instead of computing the x squared, it computes the gradient of this function. So the gradient of this function is 2 times x. So this jax.grad takes in a function as input. This is not a value or anything like this. This is a native Python function. And the object that it returns is another native Python function that, when you call that function, gives you the gradient of the original function. So this is a program transformation. It takes a program, or generally a function in Python, and returns a new function. Who's with me? Yeah, go on. It's an operator. It's an operator. Yeah, it's an operator. Yeah. If in a mathematical sense, yeah. Did you have a question? That's okay. So let me just enumerate that for you. We just create an array with a value of x in it here. If we print the value of, we call this function, this new transform function, and we print the value of the gradient, and we get 20, so 2 times x. So what's really nice is we can then call that, we can take that function and call it with some other value, and we'll get the gradient for some other value of x. So how is this different to PyTorch or TensorFlow 2.0? How does PyTorch compute gradients or do autograd? Yeah, go on. So how would you get the gradient of f of x with PyTorch? Yes. Yeah. So PyTorch doesn't give you this like function that you can evaluate at any point in x. What it does is you define a specific value of x, you do a computation on that value, and then you call autograd back through the computational graphs to get the gradient at that value. So it's slightly different. So each time you'll have to create a new value of x, do a new computation on x, and then call back up again. Yeah.
Isn't creating the background also the tree that forms the graph tree? So is it actually the same as finding the values of the tree that graph?
Yes. Yes, it is. It is the same, but we get the function explicitly. So we can carry it around in our code, and we can apply it elsewhere, which is maybe more powerful than PyTorch, because that's like a function that we can evaluate. By the way, JAX, I think PyTorch also has this kind of program transformation ability now. This is kind of the latest stuff they're working on in PyTorch. So that's also something to note as well. So how does it actually do this? So this is where JAX is actually, in my opinion, like a technical marvel. How it actually does this behind the scenes is very impressive. And what it does is it actually takes this native Python function that we defined, and it turns it into a simpler, more intermediate language, which is JAX's own language called JAX-PR. So it's kind of a lower level representation of this function. Again, I'm not going to go into the details of this language, but you can see that it's just rewriting this function and turning it into something that looks a bit more low level, with kind of types defined in other things like this. Once it's got that intermediate representation, then it applies the transformation directly to this intermediate representation. And it will produce a new function. And if you look at the intermediate representation of that function, you can see that function is, the exact function that computes the gradient. If you look at that long enough, you can see it's just doing kind of 2 times x. and giving you the gradient. So yeah, it really is giving you the function that you evaluate to get the gradient, you know, to x. Okay. So this is what a program transformation is. It's transforming one program to another program. And the way that JAX does it is it treats the lines of code here that you actually wrote as data and transforms that into a new function. So this is known as kind of meta programming. It's like programs that write new programs. It's not just doing array computation. It's like taking in an actual lines of code and spitting out new lines of code. Everyone now understand what a program transformation is? Okay. So this is where JAX gets really powerful, is that once you've spit out a new function, again, this is a native Python function, we can take that function and then apply some other separate transform to it and do the same process recursively if we like. And so this is the power of JAX, is that these program transformations can be arbitrarily composed. So a simple extra transformation we might do is take this function that is just computing 2x, and we just call jax.grad again to get the function that computes the gradient of that function, which is just 2. So if we call this new function, again, we can query it at any point in x. We'll get the second order derivative of the original function. So this is really, really nice. I would argue a much clearer or kind of explicit way of computing gradients and doing autograph. So this is going to allow us to develop some very highly sophisticated kind of workflows using this idea of arbitrary composition of function transformations. Does this make sense to everyone how this works? Yeah.
And that the grad function, like analytic rules, how to transform.
No, it doesn't. So it's not. It doesn't use analytic rules. Or is it? So we talked about auto differentiation, and we talked about vector Jacobian products, and I talked you through the algorithm that computes vector Jacobian products, where you basically define the forward operation, but for each primitive operation, you also define the vector Jacobian product, and then as you do a forward pass and then a backward pass, and that will give you the gradient. And so this is actually exactly what it's doing here. If you look at this transformed function, it's doing the vector Jacobian product computation. So it's doing like a forward product here, and then it's doing the backprop through that, the vector Jacobian products through that. So that's what grad is actually doing. This is writing the whole autograd computation down as a function. Okay. So I'm going to do some coding. You can follow the link if you like. Yeah, if you want to grab it, you can. So this is a notebook that you can go through. It's a very basic introductory notebook on JAX. So if I just change my screen. So I'm just going to show you some of what we've already covered just in this notebook. So we're just going to import JAX like we just import any other Python library. And again, this is just an example of doing some very basic array computation in JAX. And like I said, we just create an array just like we would do in NumPy, and then just do some basic array multiplication or element-wise operation here. The other thing that's happening here is X is just a 1x3 array here. So who's heard of broadcasting? Who's used broadcasting in NumPy? Yeah, this is where you have like a 1 in. If you have a dimension size which is 1, it can kind of parallelize that across another computation or broadcast it in general. So that's what it's actually doing here when it's creating this array. So all of that kind of clever broadcasting stuff in NumPy is also in JAX. So what we're going to do here is we're just going to do auto differentiation with JAX, just like I showed you. So this time I've got tan h. This is my function that I'm going to differentiate. So if I just plot this for I've got a vector here of x values from -5 to 5. So this is the 10H. So what I'm going to do is just use the program transformation to transform this function into its gradient. So it's very simple. We just say df dx. Again, this is a Python function that's going to be output is jax.grad of my function. And we also want to compute the second order derivative. So it's very simple. All we do is just call jax.grad again. So on this new function. And again, we return a new function which evaluates the second order derivative. So we say df d2f dx2 function equals jax.grad on this guy. And then we run this. And then all we're doing here is plotting the result across the X array, and you see JAX is giving us the gradient and the second order derivative of tan H. So that's just showing you, how easy it is to do autograd in JAX. Okay. Yeah.
It's going to do like multi-dimensional derivatives.
Yeah. Yeah. So I'm passing over the fact that jax.grad expects the output of the function to be scalar. So it's the scalar gradient of a function. Or it's the gradient of a scalar function. The function can have vector inputs. So it's doing the vector Jacobian product, but in that case, the vector that we're multiplying the Jacobian by is just a simple scalar, and it's defined as 1. I'm going to talk about right now the lower level, other JAX transformations, which can do the VJP in general and the JVP in general. So this is why I'm having to do a for loop here, because I have to make sure that the input is scalar. Okay. Okay, so okay. Just check that you can see my screen. Okay. So I just showed you the gradient, which does the gradient for a scalar, a function that outputs a scalar. But in general, JAX can do vector Jacobian products and Jacobian vector products, as I was describing in the auto differentiation lectures. And in fact, all of JAX's auto differentiations program transformations are all based on compositions of the VJP and JVP. They're just specializations or compositions of these two fundamental kind of program transformations. So we can do things like get the gradient of f. We can even get the Jacobian of f. So all the derivatives of all the partial derivative of f with respect to its inputs. We can get the Hessian. We can do all sorts of really interesting things, and you can go back and have a look at how these the inputs and outputs of these program transformations later. So yeah, computing the gradient, doing autodiff is just one type of program transformation. This is actually a much more general idea than just using it for autodiff. So can anyone think of any other useful transformations we might want to make of some, if we define some function in Python, what might be a transformation that's useful? Yeah.
Maybe it's kind of inverse transformation.
Yeah, that's actually quite a good idea. Yeah, invert the functions. So instead of f of x, it does x function of f. Yeah. So JAX doesn't have that, but that would be interesting. Yeah. Any basis transformation? Yeah, that's a good idea. Yeah. Any others? Yeah. Integration? Yeah, very, very good. Yeah. So I'm going to talk about some other ones. So one is just to vectorize the function. So this is a very powerful transformation in JAX. And vectorization is, you can think of it as simply just parallelizing the function across many inputs. But when I mean that, I don't mean parallelizing it across multiple kind of devices, multiple CPUs and multiple GPUs. I just mean parallelizing it so it runs in parallel on the single device, so on the GPU in parallel. So what I mean by that is, say for example, we have this like basic computation here, which is just a dot product between two vectors plus some bias. Like, this is a very common operation used in like linear layers of neural networks and other scientific workflows. So say now that I give you many examples of X, and I want to times all those examples by the same weight value. Mathematically, we can just think of that as a vector times by a matrix operation instead of a dot product that will spit out a vector instead of a scalar. And so the task here is to take the code, the function that just computes a single, for a single example, the dot product, and give you a scalar. And we might want to vectorize that function and say, okay, we now want to, instead of just inputting a single X to that, X will now have another dimension, which will contain all the examples, all the parallel examples we want to run that computation over. Everyone follow so far? So if we were just going to write this in NumPy, we would have to think about, okay, X has changed dimensionality. We're going to have to change this dot product with a matrix multiply, or make sure that NumPy understands that there's an extra dimension to X. But JAX means that you can forget about that. You can just write your function for a single example, and then what you do is you just call jax.vmap. So this is vectorized map. Again, it's another function transformation. It takes my function as input, any arbitrary Python function, and you tell it, of the three inputs that it have, which inputs you want to parallelize across, and more specifically, which dimension of that input we're gonna denote as having all these parallel inputs, or these examples in it. So what this function fbatch is going to say is it's going to take W as input, it's going to take B as input, but then it's going to take X with an extra dimension added on the first dimension that contains all the examples that we're going to run in parallel of X. So now if we create X here with an extra dimension with all these examples of these vectors that we want to compute, and we print the output of fbatch, you can see that it's now giving us a vector as output instead of a scalar. So it's doing all these in parallel. Yeah.
So vmap can vectorize JAX NumPy functions. So like, yeah, if else statements, and then you have to rewrite it like this.
VMAP can handle if-else statements. So there's some subtleties which I don't have time to talk about, but there's one of the limitations of JAX is that the shapes of the output shouldn't depend on the values of the input. So what I'm saying is the shape should be known statically before you input them to the given the shapes of the inputs of the function. If you can do that and make sure that it's a static computation, then you can use kind of conditional statements and still vectorize those statements. Yeah. Yeah. I think that's true, but it depends on the program transformation. That's definitely true for compilation. I think that's true for vectorization, but I'd have to actually check properly. So if you look at the kind of, again, if we look at the intermediate representation, this is, again, to transform this function, JAX will take this intermediate representation and then treat it as input, as data as input, and spit out a new function, which is the vectorized format. And if you go into this function and actually look what it's doing, it's inside here, it's got like a dot product, this dot general here in the original function, which is what numpy dot is doing. But what's interesting is that when we vmapped it, it's realized that we can still do this as a dot product. This is now, instead of a vector dot product, this is now a matrix kind of product instead. And this generalized dot product can handle that. So what's cool is that it's not using like a for loop. Like the naive way of vectorizing this function would just be to say for I in range n, call this function with each new X as input. It's realized that we don't need to do that. We can actually just write it as a matrix product. And this is what, when we run that matrix product on the GPU, it will then use the cores in parallel to do the computation. So this vectorized function is much faster than just doing like a native Python for loop to call the function repeatedly. Does that make sense? Okay. So let's go back and look at that. So oh, I do have a couple more examples about autodiff. So this, for example, this is let's just go back to this autodiff example. So this is doing the tanh function, computing tanh. So we can do JAX.Jacobian. This will give us the Jacobian of that function. Again, this is a function that we call with a value of x, and it will spit out the Jacobian. So the Jacobian is a matrix. It's all the partial derivatives of f with respect to x. And now x here is an array that we're inputting. So it's a x in the range -5 to 5. And what it spits out is an array that is diagonal, like a Jacobian that's diagonal. So can anyone tell me why this Jacobian is diagonal in this case? For a function that takes in x and spits out tanh x? Yeah. Yeah. So when you call this function with a vector, it outputs a vector. So JAX sees that as like a vector valued function that has a vector input. So the Jacobian of that in general would be a matrix. But the important thing is that each output of that function only depends on the same element in the input. So, you know, f1 only depends on x1, f2 only depends on x2. So there's the gradients of all the cross derivatives, of all the cross partial derivatives are just 0 because it's an element-wise operation. So yeah, the Jacobian in this case is diagonal. So yeah, and we can also do you know, vector Jacobian products. So now x is an array. So we do a vector Jacobian product. We define the vector as an array of ones, and this will just give us the gradient, element-wise gradient. And we can do the same thing with the forward mode autodiff instead. And again, that will give us the gradient, the same gradient. So you can have a go, you can look through this again in your own time and just convince yourself what's happening mathematically here. Okay. So let's talk about vectorization. So let's vectorize this function. So now we're going to vectorize not just this kind of simple dot product, or actually this is now a matrix vector multiply. We're assuming this is like a layer of a fully connected network. So we have a weight matrix, we have a single example, x is a vector. We're going to add a bias vector, and then we're going to pass it through an activation function. So we can call vmap on this entire function and allow it or vectorize it or parallelize it across many examples of x. So this is just if I just call the function with some random kind of weight matrix, 10 by 3 weight matrix, and an x vector that has 3 elements, then yeah, the input size of x is just a vector with 3 elements. The output of the function is a vector with 10 elements. So this would be the hidden state after the layer. But say that I have many examples of x instead. So maybe I've got 1,000 examples, like a batch of training examples that I'd be feeding to the network. So all we do to vectorize this function is we just do just call jax.vmap on this function. So we grab the function and we say which axes and which arguments we want to parallelize across. So if we don't want to parallelize across any of the arguments, then we'll just put a none. So just saying that we're not going to parallelize for the first 2 arguments. And then for the last one, we're just going to say the examples are in the first dimension of the input. And then again, when we run this function forwards with a batched example, then we get a batch of outputs. So you can see how this can become very powerful when we have very complicated functions. We can vectorize the whole function across all the NumPy operations that we have in our function. Okay. So let me swap again. Okay, so next type of program transformation is a compilation. So I'm not going to go into details about how JAX is doing compilation. I'll give maybe one example, but at a very high level, you can just think of this as taking my original Python code and just rewriting it using this lower level representation and also XLA, this accelerated linear algebra compiler, to make it run faster on the specific device that you're using. And so this is an example of how we might make this code a bit faster. So this is a function that just computes x plus x squared plus x cubed. And the way that this function might run on the GPU, if you just call it this way in JAX, is there are separate kind of underlying CUDA kernels. These are kind of like low-level pieces of code that are defined to run like small operations very fast. So there might be a CUDA kernel that is defined for like a simple matrix multiply or an element-wise multiplication, like an x squared. There might be another kernel, which is a different implementation that runs x cubed. And then there might be a final kernel that is called to sum all these things together. And if the code uses separate kernels, then usually what happens is that each kernel runs independent. There's like an independent thread or kind of job on the GPU. It reads from the kind of global memory of the GPU for its inputs and then saves those outputs of that individual kernel back to the memory, back to the global memory of the GPU. So this is the kind of shared memory across all the cores. So what takes time in this whole operation is the reading and writing to the global memory. This is the kind of bottleneck of these computations. When you call JAX compilation, it realizes that these three kernels can actually be fused into a single kernel. So it kind of writes a kind of custom kernel or a fused kernel that doesn't have to do all these kind of reads and writes to the memory. It knows that I can just do one read to the memory of X. I can do all these X computations and sum them together without having to save and rewrite to the memory. So it kind of minimizes these communication steps and gives you a fused kernel when you compile the code. So this is just one example of how this is a function transformation. It takes your function and gives you a compiled version of that function that runs very fast. This is just one example of how JIT optimizes the code. JIT does many other very sophisticated optimizations with XLA that I'm not going to talk about. Long story short, once you've JITted your code and you've compiled it, it often runs much faster. So for example, when we fuse these operations together, we can just get a speed up of 8 times already. So, by reducing the bottleneck of read and write to the global memory. So yeah, behind the scenes, this is using XLA, accelerated linear algebra, both for the CPU and GPU, and I think it works for other specialized devices too, like TPUs and other devices. But there is a cost here, and the cost is that it takes time to compile the function. It depends on the function, but sometimes this can take seconds or more. And this is kind of an upfront cost is to do that compilation. So typically you'll only kind of compile functions that you're going to run hundreds of times, so that upfront cost is kind of amortized or is not important. So if you imagine like training a deep neural network, one function that we call thousands of times is the function that does the update of the network's weights. So it does the gradient descent step. So when we use JAX compilation in deep learning, usually we compile the update step, and that's expensive for the first update, but then for the next million updates is very fast. Any questions on this? Okay. So I'll just go back to the JIT compilation and then we'll take a break. So yeah, here's an example of exactly that function. Just to prove to you that if I compile that function, then I time how long it takes to run that function for a fairly large array. This is running on my CPU, by the way, so I'm not even on a GPU, but the compilation still makes the CPU run much faster. So this is going to take, this is about an 8 times speed up, like I was showing in the slides. when I'm calling the JIT function rather than the original function. Okay, so I'm going to describe. I think we'll take a break and then I'll describe the final example. We're going to put all these ideas together to do some linear regression. So, yep. Okay, so let's carry on. We're going to put this all together, all these concepts that we've learned about program transformations, and do linear regression. And you're going to see that this task is going to use all of these transformations. So we're going to use the VMAP, we're going to use JIT compilation, we're going to use the grad transformation all together and compose them together to solve this. So here's our training data. We just want to fit a straight line to this data. That's what we're going to do in one dimension. So first of all, I'm just going to define a function that gives us our initial guess of what our weight and our bias value is. This is just the gradient and the intercept of the line. They're both scalar values. So we're going to use gradient descent to solve linear regression. Obviously, we can do it more analytically, but this is just for the purpose of demonstration. So then this is our forward model. Like we would do in PyTorch, we would define like a forward function. So we're just going to grab our weight bias value. We're going to do the matrix multiplier with x, which is simply just a dot product, or in fact, it's just a single scalar times by a single scalar in this case, plus a bias. And then I've got I'm going to vmap my forward batch. So this is written for a single example, a single value of x, the scalar value in this case, because it's a 1D line. And we're going to vmap it so that it can take in all of these examples of x that we have. We have 100 different training points here. Then we're going to define a loss function, which takes the batch of x values, the labels of y, so the x and y coordinates that we have in training data. It's going to call this vmap version of the forward function, so compute the prediction for all of the training points. And then our loss function is just the prediction of the y value, the mean squared error between the labels and the prediction. Everyone follow me so far? Great. Then we're going to call this gradient transformation. So value and grad is just another program transformation that just spits out the gradient and also the value of the function at the same time. So it gives us both values. And we're going to differentiate loss with respect to the first argument. So this is going to give us dl by d theta. So this is the gradient of the loss with respect to the weights of the model. So with respect to w and b here. So then the final thing we need to do is do a gradient descent step. We need to define a function that we're going to call many, many times in a for loop to do gradient descent on the weights. So that's what I'm going to write. So to do the step, we just need to compute the gradient, and then we need to update the weights based on that gradient. So how do I compute the gradient? Yeah. So we did that already. We've got a function here, grad. This is a function. This is a program transformation. It takes loss and gives me the gradient of the loss. So all we need to do is just call that function. So we just say dl d theta equals grad, and then we pass all the arguments of the original function. So we pass all these guys to that. So like I said, this transformation not only gives you the gradient, but also just gives you the value of the loss. So we get both when we call that function. And so now we need to update theta based on the gradient of theta. So we say theta equals. So theta here is actually a tuple. It's a Python tuple, which just contains the weight and the bias values. So I need to go into that tuple and update the weight. So the output here, this dl by d theta, is also a tuple, which has the gradient of both of those quantities in it. So I need to go into that tuple and update the tuple. So JAX has like a handy kind of utility function, which is called jax.treemap. So what this does is take any kind of Python tree. So a tree would be like a nested structure, like a dictionary or a dictionary with lists in, or that has some sort of leaves at the bottom. So this tuple is also a Python, a pi tree, which JAX calls these things a pi tree. So tree map just applies some function to each of the leaves of that tree. So the function that we want to do is just a gradient descent step. So we specify what the function is. So the function is going to take the theta value and the gradient like this, and it's going to say we're going to take a gradient descent step by timesing the gradient by a small value, and then we're going to map this function to the theta tree and the gradient tree like this. So can you see how what we're just going through here is we're just going through these tuples and updating the gradients of each of the elements of the tuple. That's what we're doing. And then we just need to return the theta and the loss value like this. So this is performing one gradient descent step, and then what we have here is just a for loop which is going to call that step function many times. Before we call it, we're actually going to use JIT to compile this function. So this is what I was saying. We typically, when we're training models, we compile the highest level function we can, which in this case is the function that does the gradient descent step. Any questions on this before I run it? Okay. So if you run it and it does it straight away. It's this is why JIT is so powerful. It just runs so quickly on these like small operations. So I just ran 1,000 gradient descent steps and it did it basically instantly on my CPU. And we fit the line. Okay. So let's go back to the slides. Okay. So I talked about the kind of fundamental features of JAX, the accelerated array computation and the program transformation in a very general way. And these things can help us do big machine learning tasks, but there is also a lot of effort using JAX for scientific machine learning tasks. So doing exactly the types of techniques that we've been studying in this course, combining machine learning very tightly with our scientific computing algorithms that we have already. And these are just some of the libraries that have been built on top of JAX that help us do these kind of SciML kind of type tasks. So there's optimization libraries for doing, gradient descent and higher order kind of optimization methods, OpTax, JAX-Op, Optimistics. There are many libraries out there. There are also other libraries that allow you to train neural networks and define neural network architectures. So JAX is maybe a bit different to PyTorch in this respect. JAX doesn't have like a built-in module that does neural networks. You have to use one of these kind of external libraries to do that. There's go on.
JAX and PyTorch together, like we described beforehand.
Yeah.
And they somehow interfere with each other.
So the question is, can you combine PyTorch and JAX together? I think it would be difficult because of the way they do autograd very fundamentally different, where PyTorch defines its own version of an array or a PyTorch tensor, which has this gradient attribute. So to convert that to a JAX array would probably be quite difficult inside of some hybrid autograd code. But what you could do, if there's like some pre-processing step, or if there's like some other thing that doesn't need PyTorch gradients, it's just like a brute force computation. You could offload that to a JIT compiled JAX code that spits out an array that then PyTorch can just convert into a PyTorch tensor. So yeah, there's maybe ways, yeah.
Maybe possible to transform a PyTorch model to one of these tracks, flex.
Yeah, I don't know actually if there's like a library that converts between libraries. Yeah. Yeah. I'm not sure. Maybe. But, so these libraries are certainly not as developed as PyTorch. So this goes back to your question before, my advice about should I use PyTorch or should I use JAX? I think both libraries are brilliant. Just to learn both libraries is very useful for you to kind of develop. But yeah, in general, I would use PyTorch to do kind of standard deep learning tasks where I want to train like a standard neural network. But I would use JAX if I want to do something more complicated where I want like more complex derivatives, if I want to combine forward mode with reverse mode, autodiff, if I want to do Hessians, if I want to do parallelism across multiple devices, etc. And also if I want to compose all this stuff. Okay, so scientific computing. So there are also libraries that can do, you know, the types of stuff that we need to do in scientific computing. So things like matrix solves or linear algebra computations. Diffrax is an amazing library that allows you to train neural differential equations. So to solve ODEs and also SDEs, and also define learnable components of those and backprop through them, just like we were talking about in the neural differential equation lectures. There's JAX.scipy, which does tries to. It's not a full set of NumPy of the original SciPy library, but it has some of the functionality. And then there are a lot of amazing SciML libraries. Some of you might have been talking about these before. So, for example, JAX-MD is a highly performant library from molecular dynamics. Brax again is this rigid body simulation in JAX. NumPyro is a probabilistic programming language, so doing like Bayesian inference using JAX, super interesting. JAX-CFD, computational fluid dynamics on GPUs, pretty cool. DeepXDD is a PINS library or a physics-informed machine learning library. So there's a lot of really cool stuff happening in this SciML ecosystem. So the final example that I want to end on is to show you an example of using optimization in JAX and using the optax library. So this is a library that's often used for gradient descent in JAX. And I just want to show you how easy it is to solve a scientific problem. I'm not doing any machine learning here. I'm just trying to solve the inverse problem for this wave equation example. So what's the inverse problem? Is to say, if I give you an example of what the wave field is at some time, can I guess what the underlying velocity model is that earthquake or seismic wave propagated through? And so we can frame that as an optimization problem. We can start with some guess of what the velocity model is, and we would just maybe start with a smooth version of what we might think it is. And then we can just run the forward simulator, call the finite difference simulator to predict what the estimated wave field is, and then have a loss function which matches the estimated wave field to the true wave field. Use JAX's autograd to get the gradient of that loss function with respect to the velocity model, and then update the velocity model using gradient descent. This is like a standard optimization algorithm for this like inverse problem. And what's nice, I already showed you the code for doing the forward simulation. It was like maybe 50 lines of code, like basic NumPy code. This is all that I need to add to be able to solve the inverse problem. I just define the loss function, which takes in my guess of the velocity and the true wave field measurements here. Calls the forward function. So this calls that finite difference solver to get the estimated wave field. And then we just match the estimated wave field to the true wave field. And this is where JAX really kicks in, is we can then call JAX.grad on our loss to give us our gradient function. And we just define an optimizer in optax, the Adam optimizer. So again, we can use kind of modern deep learning optimizers to solve this inverse problem. And then update the gradients. We can also compile this. I haven't written JAX compilation, but we can compile the update function just like we did before. And yeah, just with like maybe 10 extra lines of code, we can solve this inverse problem. So super powerful. To have written this by hand, to write the gradients out by hand would have taken a lot more effort to do. And this is running in a very performant way, very, very quickly. Remember, each forward simulation here is only taking 65 milliseconds on the GPU. Okay. Anyone know why the estimated velocity is only fills in the circle? Go on. Yeah, because the true wave field here only propagates to that point here. And so there's no information. The waves haven't traveled through this part of the velocity, so we could never understand what the velocity is in this part. Yeah, it's just problem-specific behavior. Okay. So there's my high-level pitch for JAX. There are other great options. So another option people compare to is Julia. Julia is a whole other programming language that has kind of other functionality which is similar to JAX. I'm just more familiar with JAX, but I encourage you to explore different languages and different options for your tasks that you want to solve. But yeah, JAX is an accelerated array computation and program transformation, and autodiff, vectorisation, compilation can all be thought of as program transformations and are available to use in JAX. And JAX really does enable this kind of high performance, large scale sign-up. So that's the end of this lecture. Any questions before? I'm going to start the next one now.